Hello and welcome to this episode of AP Daily. Today we're going to be covering topic 7.12, the common ion effect. We're going to be learning to identify the solubility of salt and or the value of KSP, which is the solubility constant for the salt, based on the concentration of a common ion already present in the solution. We're going to learn what the common ion effect is, the logic behind it, and we're also going to do 3 example problems that use it. My name is Eleanor Flanagan. I'm an AP chemistry student and I'm a junior at Bayport High School in Green Bay, Wisconsin. Okay, let's start with some information that we already know. We know that we can classify ionic compounds as soluble or insoluble, and we know that the dissolution of a salt is a reversible process. We can measure the rate of this process using KSP, or the solubility constant, and we can calculate this constant by placing the concentration of the products over the concentration of the reactants. Quick note here that this is in molars and not moles, so we use moles per liter. And also another note, we exclude the solids in dissolutions because we don't have to use them to figure out the solubility constant. So let's look at how adding ions, including in the salt, which are called common ions, influences the reaction rate. This is a sample reaction of silver chloride dissolving into its ions, and it's not completely soluble, so we have a reversible reaction. We know that this solution is saturated, which means at this point there is like the maximum amount of ions in the solute, and adding any more solute will cause a part of the reaction to precipitate back into a solid. So we basically have the maximum amount of solute that is dissolved in here. Here, I have added sodium chloride to the reaction, and sodium salts are 100% soluble. So this sodium chloride is going to dissolve completely with our silver chloride. And you'll note that the chloride ion is a product here. So we can use Le Chatelier's principle to figure out what might happen. When sodium chloride is added and dissolved, there now becomes more product. We've already covered this. All sodium salts are 100% soluble. So at this point, the reaction constant, or the reaction rate, QSP, is bigger than the reaction constant, KSP. And we know that from Le Chatelier's principle, the reaction will now shift to the left and form more solid because the reaction is oversaturated with sodium chloride. But the sodium chloride kind of replaces the silver here because it is more soluble. So in the presence of a common ion, the solubility decreases. Let's do an example problem. Pause it here if you would like to try it yourself. Okay, and we're back. So we're being asked, how would the results of the experiment be altered if we mixed excess silver chloride with tap water that already had chloride ions in it? So, okay, let's go through this logically. We are given in the problem that the solution will have silver chloride that the student added, and we were also given that the solution has excess chloride ions because it is tap water. And we know that these chloride ions are a product of the dissolution. Any excess common ion causes the reaction to be less soluble. We already proved this. So if the salt is less soluble, the solubility constant will be lower. So the conclusion is that KSP will appear lower, and the KSP value will be too small because the silver chloride will dissolve less when the chloride ion is in the water due to the common ion effect. Okay, let's do another example problem. I will give you time to pause. Okay, so to solve this one, we are given that we are being asked what the molar solubility is in pure water, and we are also being asked what the addition of sodium chloride has on this solubility. So in this reaction here, we are given that it is a saturated solution. So we've been over this before. That means that there is like the maximum amount of ions in the solute. But we also know that sodium fluoride is 100% soluble. So it will kind of replace some of the cadmium fluoride here, or the cadmium fluorine ions when it is dissolved. So recall molar solubility. We know that the molar solubility is the maximum solute that can be in the reaction before it becomes saturated. So that is at its saturation point. We are given that the solution is saturated here, and we also have the molar quantities of these two products here, the cadmium ion and the fluorine ion, at its saturation point. So per liter here. But so if we are given the molar quantities for the reactant, we can use these quantities and we can use mole ratios to figure out what the saturation or what the molar solubility of this product is here, the cadmium fluoride. So because it is a 1-to-1 ratio of cadmium ion and cadmium fluoride, we can conclude that 0.0585 must be our answer. And we also know that adding a common ion decreases solubility for the second part of our question here. So what is our conclusion? The molar solubility of cadmium fluoride is 0.0585 molar, and the addition of sodium fluoride will decrease the solubility. Okay, and our other example problem, I will give you time to pause here. All right, and we're back. So we are being asked how many moles of sodium fluoride must be dissolved in 1 liter of a saturated solution of lead fluoride to reduce the amount of lead ion to 1 times 10 to the negative 6 molar. And we are also given the KSP for this dissolution reaction here. Okay, so here is the work that I used. I set the KSP equal to the concentration of each of these ions here. And we know that at our final point, we are given the concentration of lead. So I add that there, and then you can solve for the concentration of the fluorine ion. Also, what we have to do is figure out we can use mole ratios. So this equation here, this work here, gives us the amount of fluorine in moles per liters at this point in the equation. So we can solve for the molar amount, the total molar amount of fluorine by turning this from molars to moles. We are given that we have 1 liter of our solution. So after that, we have to multiply it by the mole ratio of sodium fluoride to fluoride, and we know that this is a 1-to-1 ratio, to get 2 moles of sodium fluoride. So that is part of our answer. A couple notes that when dissociated, fluorine is not diatomic, so it's 2 fluoride ions and not diatomic fluorine. Mole ratios should be used to find the correct amount. We just explained that. And again, the solution is saturated. And that is our final answer again. Let's go over a summary of what we learned and what is important we should know. The solubility of a salt is reduced when it is dissolved into a solution that already contains one of the ions present in the salt. The impact of this common ion effect on solubility can be understood qualitatively using Le Chatelier's principle or calculated from the KSP, which is the solubility constant of the dissolution process. The solubility constant is calculated by multiplying the concentration of the ions. A saturated solution is a solution where the solvent is at maximum capacity, and a molar solubility is the amount of moles in a solution that can contain that the solution can contain before the solvent precipitates out of the solution. Okay, and that is it for 7.12. I hope you found this helpful and not too confusing. That is it for me. Thank you for watching.